This study explored innovative way to utilize red mud and industrial waste to develop sustainable geopolymer building material with enhanced performance and reduced environmental impacts. Ordinary Portland cement production is a major contributor to global CO2 emission, as we all know. To mitigate these, researchers have explored geopolymers, material synthesized by the condensation of tetrahedral silicoaluminate units activated by alkaline solution. Geopolymers offer advantages such as a high energy strength, corrosion resistance, and durability while significantly reducing energy use and carbon emission compared to cement. However, conventional precursors like fly ash and slag are being expensive and less available, prompting exploration of alternative material. In this study investigate how changing silica alumina molar ratio from 2.25 to 3.0 and the partial replacement of red mud with ground granulated blast-furnace slag affect the properties of geopolymers. Key properties analyzed including fresh characteristics like flowability and setting time, as well as mechanical strength, shrinkages, water permeability, microstructural features, and environmental impact in terms of CO2 emission and cost. The material used were red mud and GGBS sourced uh, locally. Red mud is highly alkaline aluminosilicate industrial waste and GGBS is calcium rich byproduct. So sodium hydroxide and sodium silicate solutions serve as a alkaline activators. Mixtures were prepared in two groups, one varying the SiO2 L2O3 ratio with fixed other ratio, the other increasing GGBS content to partially replace red mud. Samples were cast into 40 cubes, vibrated to remove air, covered to prevent moisture loss, and cured in controlled temperature and humidity environments. Various tests were conducted to characterize the geopolymers. Flowability was tested by measuring the spread of freshly mixed paste. Setting times were determined using a Vicat needle. The compressive strength measured on 40 cubes after curing for various duration. Drying, shrinkage and water permeability were also assessed. Microstructure analysis employed SEM EDS imaging, FTIR spectroscopy, XRD for mineral phases, and TZDTD for thermal decomposition characteristics. The fresh properties showed that increasing silica alumina ratio or adding more GGBS reduced flowability. This is because higher silicate concentrate increase viscosity and accelerate polycondensation reaction, forming a dense gel network. Setting times also shorten under these conditions due to faster geopolymerization facilitated by availability of reactive silicate and calcium ions. Compressive strength improved with both higher silica alumina ratio and increased GGBS content. So this is a very important finding. The 56-day strength grew by up to 16.1% with increased silicate and up to 8.9% with slag addition. Drying shrinkage was reduced by 22% and 14% respectively, while water permeability also decreased, indicating denser, less porous microstructure. Microstructure analysis revealed that higher silica alumina ratio promoted the formation of a highly polymerized dense cast gel. network. FTIR and XRD confirm enhanced gel formation and reduced unreacted quartz and carbonate phase. SEM EDS image showed fewer cracks and smaller pores. TZDTG demonstrated increased hydration products. All these points towards denser, stronger matrix promoted by optimized molar ratio and slag content. Environmental and economic assessment indicated that the optimized geopolymer reduced CO2 emission by 13 to 44% and lowered cost up to nearly 40% compared to similar RM-based geopolymers. The silica-alumina ratio played a critical role in controlling emission with moderate increase in silica content, promoting strength and reducing carbon footprint. However, higher GGBS content while enhancing properties can increase cost. Thus, balance is essential. So, in conclusion, this study show that increasing silica-alumina ratio and incorporating more GGBS accelerate gel network formation, improving strength and reducing setting time and flowability. Enhanced formation of a hydration gels also reduce drying shrinkage and water permeability. Microstructural densification with increased calcium by silica and silicon aluminum ratio further strengthen the materials. Optimized red mud based geopolymers demonstrate substantially reduced CO2 emission and lower cost, supporting sustainable building material development.